Hi, today I'm going to talk about thermal calculations and thermal lump model of power electronic circuits for EE463 Static Power Conversion 1 course. For this tutorial, I'm going to construct a buck converter with following parameters. It has a 24 volts of input voltage, it has 5 volts of output voltage and 25 watts of output power. The switching frequency of the MOSFET is chosen as 100 kHz. I'm not going to go into detail of choosing the buck converter circuit parameters since it's not in the scope of this tutorial. I have chosen a MOSFET for this application, an N-channel MOSFET. It has a drain source voltage of 100 volts and it has an RDS on-state resistance of 0.54 ohm. It has a TO220 package which is going to be used in following slides. And what's important in the datasheet of this MOSFET is the thermal resistance ratings. You can see on the first row the junction to ambient thermal resistance. Now this junction to ambient thermal resistance is used in cases which doesn't have a heatsink connected to the case of the MOSFET, and we have case to heatsink and junction to case thermal resistances, which is going to be used in heatsink, the thermal model with the heatsink. Now before moving on to the thermal calculations, first we need to calculate the power losses on the MOSFET. Now there are two types of power losses. First is the conduction loss and the second is the switching loss. In order to calculate the conduction loss, we can use this following formula. We can multiply the RDS on with the square of the output current and with the duty cycle, or we can simply multiply the RDS on with the RMS of the current passing through the MOSFET. Both of them give the same result, which results in the 2.8 watts of power loss due to the conduction in the MOSFET. After calculating the conduction losses, we should calculate the switching loss. Switching loss can be calculated using these formulas. The input voltage, the maximum input voltage, which is the input voltage in our case, DC voltage. The output current is multiplied with the switching frequency and the rise and fall time of the MOSFET, which is specified on the datasheet of the MOSFET. Or you can multiply these same parameters with the gate source and gate drain charge divided by the gate current. This also gives the rise and fall time of the MOSFET, but since we do not know the gate current, it's easier to use in our case the rise and fall time. But if you are implementing it on a specified gate current, this can be more accurate. This can give a more accurate switching loss results. After inserting the required parameters, we have found that the switching loss is around 0.6 watts. That results a total power loss of 3.4 watts of power. Now we can move on to the thermal part of the tutorial. Now in this part, I did not calculate the power losses on the diode and other circuit parameters. I have just focused on the MOSFET, but the rest are the same as we will do in the MOSFET. In the first case, I have focused on a system without a heatsink. So it is just a MOSFET without a heatsink connected to the case of the MOSFET. The thermal model of the system is given as on the right hand side. We have a heat source which is the total loss of conduction and switching losses. We have a junction to ambient thermal resistance, and we have the thermal ambient temperature of the ambient, which changes depending upon the temperature, depending upon the temperature standards that you are going to use. There are different standards for different applications. For commercial applications, the ambient temperature can be chosen between 0 and 70 Celsius. So if you're producing a product for commercial purposes, your product should work in these temperature range. But if you are producing a product for industrial applications, then it should work between -40 to 85 Celsius. But if you are producing a product for military purposes, then it should work between -55 to 125 Celsius, which creates a little bit of challenge in regards of cooling or heating the power electronic circuits. So what we are trying to do in thermal calculations is that we are trying to minimize this thermal resistance, because if we minimize the thermal resistance, the junction temperature will be same as the ambient temperature. So our switching device can operate without any problem. In the first part, as I said, I'm going to use the case without heatsink. Our total losses is around 3.4 watts, and the junction to ambient thermal resistance is given as 62 Celsius per watt in the datasheet of the MOSFET. And assuming an ambient temperature of room temperature, which is around 25 Celsius, one can find the junction temperature of the MOSFET using this formula. As I said, junction temperature is 25 Celsius, and the losses of 3.4 watts of power results in a temperature rise of 210, which is a lot if you are constructing a commercial product, but if you are constructing a barbecue, it may be okay. So what we should do is we should use a heatsink, because we have seen that we cannot operate this circuit without a heatsink. When we add a heatsink, the thermal model changes a little bit. We have a heat source again. This power loss component represents the conduction and switching losses on the MOSFET. We have different thermal resistances this time. We have junction to case thermal resistances. Now this junction to case thermal resistance, we cannot change this parameter. It is specified in datasheet of the manufacturer. The next parameter is case to heatsink thermal resistance. Case to heatsink thermal resistance can be changed using different thermal interface materials, but a typical value of case to heatsink thermal resistance is given in the datasheet. And the last parameter is the heatsink to ambient thermal resistance. Now this is a very critical parameter that we are going to choose in the following slides. Now this thermal model represents the physical model on the right hand side. This white box represents the junction of the MOSFET. Now this is the heat source where the heat is generated in our switching device. This black one is the case of the MOSFET. Now as I said, junction to case thermal resistance cannot be changed. It is specified in the data sheets, but what we can change is after this point, we can change case to heatsink thermal resistance and heatsink to ambient thermal resistance. Again, what we are trying to do is we are trying to minimize this total thermal resistance so that we can have a cool junction temperature to safely operate our switching device. The first thing that we are going to focus on is the case to heatsink thermal resistance. In order to reduce the case to heatsink thermal resistance, we are using a material called thermal interface material, or shortly TIM. Now on the right hand side you can see two types of thermal interface materials. The first one is a thermal paste, and the second one is a thermal pad. This is like a sponge, and you apply these thermal interface materials above the case of the device, and then you put heatsink on top of this thermal interface material, and then you apply some pressure to reduce the thermal resistance between case to heatsink. Now these materials work for a few reasons. First, they fill the gaps between above this case. The cases are not ideal. They have some slots, and they have some ups and downs. So this thermal interface materials fills these gaps in order to transfer the heat between case to heatsink. And they also have a very high thermal conductivity, which results in a low thermal resistance that results in a better thermal performance. Thermal resistances are not constant like electrical resistances. In fact, electrical resistances are not constant, but they are more or less constant. But thermal resistances changes a lot. They changes with the thickness of the material. They change with the pressure applied on the material. If you increase the pressure, material thickness will reduce, so that you can have a low thermal resistance. And also they change with the material properties. For our case, I have chosen a TIM, a thermal pad, which has a part number as such, and it has a thermal conductivity of 0.7 watts per meter Kelvin. In the datasheet of the thermal pad, a table is given. In general, a table is given for most of the thermal interface materials, because, as I said, thermal resistance depends upon the pressure that you apply on the material. In the datasheet, thermal impedance versus pressure table is given for a TO220 package, which is the package that we are using in our case. As you can see, as you increase the pressure, the thermal resistance of the material reduces. In order to be on the safe side, I have chosen a thermal resistance of 0.5 Celsius per watt, which is around an applicable range of pressure. But if you are in a dire situation, then you need to apply more pressure to decrease the thermal resistance of the TIM. So we have chosen a 0.5 Celsius per watt as our case to heatsink thermal resistance. The next parameter that we are going to choose is heatsink to ambient thermal resistance. Actually, this resistance depends upon the heatsink. As I said, we are using a TO220 package of MOSFET, which is shown in the figure here. There are different kinds of packages for MOSFETs and IGBTs and diodes. Actually, they use the same package. What you can do to choose a heatsink, you should first find out the package of your switching device. Then you should find an appropriate heatsink which is suitable for your package. Our requirement for the heatsink is that we want a small volume because we have a limited amount of volume and surface area footprint on our PCB. So we don't want a huge heatsink to be put on the PCB. We want a low cost PCB, and of course finally, maybe the most important, we want a low thermal resistance from our heatsink. Okay, but what should be the thermal resistance of the heatsink? I mean, what should be the range of the thermal resistance? In order to find out, what I have done here is that I have made an assumption. We know that ambient temperature is 25 Celsius. What I have done is that I have accepted the junction temperature to be 100 Celsius. I have looked at the data sheet of the MOSFET, and it is said that it can work up to 175 Celsius of temperature. So 100 Celsius junction temperature is okay, is safe. So what I have done, we know the junction to case thermal resistance. We have found out the case to heatsink thermal resistance. We know the ambient temperature and the junction temperature. The only thing that is unknown here is the heatsink to ambient temperature. We have used this formula, and using this formula we can find out the heatsink to ambient temperature as 17 Celsius per watt. So our heatsink, in order to achieve a 100 Celsius junction temperature, heatsink to ambient thermal resistance should be lower than 17 Celsius per watt. Now this gives us a rough estimation about how our heatsink should be. I have chosen 3 different heatsinks for this tutorial. The first heatsink can be seen on the upper right hand side. It has a thermal resistance of 27.3 Celsius per watt. Of course, this is for natural cooling. I mean, if you don't, which means that if you don't apply any airflow for using fans, if you don't apply any airflow, then this is the thermal resistance of the heatsink. It has a relatively small size and volume. When we using this thermal resistance, when we calculate the junction temperature, we have found out that the junction temperature will be around 130 Celsius if we use this heatsink, which is above our set limit, which was 100 Celsius. When you look at the data sheets of the heatsinks, you generally see a graph like that. I want to go a little bit detail about this graph, because you will be seeing this graph in your personal life. So I want to go through a little bit. Now this graph actually consists of 2 different graphs. The first graph is the temperature rise versus power dissipated, and the second graph is the thermal resistance versus air velocity. Now these 2 graphs are put into a one graph paper. This line, the line which has a rising slope, it represents the temperature rise versus the power dissipated graph, and this line represents the air velocity versus thermal resistance graph. But how we are going to use this graph in our daily life? It's actually very useful and simple to use this graph. First I'm going to use the first graph line, which is the temperature rise versus power dissipated. We know that we are going to be dissipating 3.4 watts of power using this heatsink. So what we can do is that we can draw a line from this y-axis. Now before I move on, maybe I should remind you about this arrows. This arrows actually shows which lines uses which axis. For example, this line uses this axis and this y-axis, and this line uses this y-axis and this x-axis as their axes. So we can move on to the power dissipation part. So we are going to be dissipating 3.4 watts of power using this heatsink. So we are going up in the y-axis and we reach to this point, and using this point we can go to the temperature rise, and we can see that it's around 95 Celsius of a temperature rise if we use this heatsink. What does this mean? We know that the ambient temperature will be 25 Celsius. If we use this heatsink to dissipate 3.4 watts of power, the heatsink temperature will be higher than will be 95 Celsius higher than the ambient temperature. We can verify this result by using the natural cooling thermal resistance, which is given in the datasheet. We can multiply the power loss with the heatsink to ambient thermal resistance. It gives also around 93 Celsius of temperature on the heatsink, which proves the validity of the graph. The second part of the graph gives the air velocity versus thermal resistance, but we don't know the air velocity, and because we are not applying any airflow in our system for now, because we are using natural cooling most often the time. If you are using a forced cooling or airflow to cool our power electronic device, then you can use the second part of the graph. As I said before, thermal resistance is not constant value. It depends upon a lot of parameters, and air velocity is one of them. In order to observe the effect of the air velocity, I have chosen a fan, a BLDC fan, which can be seen on the right hand side. Now this fan, in the datasheets of the fans and the pumps, you see a parameter called CFM, which stands for cubic foot per minute. It's in the imperial units. In SI unit, it's equal to meter cube per second. What this value tells us that how much of air it can move in 1 minute. So 5.5 CFM means that it can move 5.5 cubic foot in a minute. We can convert this to the SI unit, and we can find that it actually creates an airflow of 1.6 meter per second airflow, this small fan. So we can use this fan to cool our heatsink. We can go back to the our graph. We have found out that 1.6 meter per second of airflow is generated using this fan, which is equal to 300 feet per minute of air velocity. So what we are going to do, we are going to go below from 300, then we are going to go right, and we can find out that our thermal resistance reduced to 8.3 Celsius per watt if we used forced cooling. Now this shows the advantage of forced cooling over natural cooling. If we use a forced cooling mechanism, we can simply reduce the thermal resistance, and we can cool the same circuit without increasing the volume of the heatsink. Thermal resistance is not constant. It depends upon the air convection rate. As you can see, if we further increase the air velocity, we can further decrease the thermal resistance to have a better thermal performance. It depends upon the surface area of the heatsink, if we increase the surface area of the heatsink, and the thermal resistance of the heatsink, the ambient thermal resistance will reduce. It also depends upon the material properties. If you're using aluminium, for example, it has a very high thermal conductivity, so it has a low thermal resistance. The second heatsink that I have chosen for this tutorial is this one. It has a thermal resistance of 9 Celsius per watt. It has a very high volume compared to the first heatsink. It has 7 times than the volume of the first one. When we calculate using the thermal resistance of this heatsink, we found out that the junction temperature is around 70 Celsius, which is below our pre-specified limit that shows this heatsink can be used in our application. Now we can use the graph again to find the temperature rise. We can go up from 3.4 watts of power and found out that the temperature rise is around 33 Celsius. The last heatsink that I have chosen for our tutorial is this one. It has a very low thermal resistance, but it has a very high volume compared to other two. When we use this heatsink, we have found out that the junction temperature reduces to 50 Celsius. It's a very cool. It's a very safe in thermal concerning thermal performance, of course. Again, using the same trick, we can find out that the temperature rise will be around 15 Celsius. The final decision on the heatsinks is as follows. If we use the first heatsink, the junction temperature of the MOSFET will be around 130 Celsius. If you want to reduce this temperature below 100 Celsius, we should use forced cooling. This heatsink has the smallest volume compared to other two heatsinks. The second one actually has a 7 times more volume than the first one, and the junction temperature of the second heatsink will be around 70 Celsius. The good thing about this heatsink is that we don't have to use a fan, so we don't have to use the forced cooling mechanism to cool our power electronic circuits. The last heatsink that we have chosen reduces the junction temperature to 50 Celsius, but this is a very high volume compared to other two heatsinks, which shows that this heatsink is an over design for this application. So I didn't choose the first heatsink since it required forced cooling. I have chosen the second heatsink, which has okay volume and a good junction temperature. I didn't choose the third heatsink since it has a very high volume compared to other two. Now this was all about our thermal calculations tutorial. Thermal calculations have a lot of tricks and tips, so it requires a very good knowledge about both mechanical properties and thermal properties and electrical properties of the materials. So just try to have a look at these tips and tricks. There are a lot of lists in the internet that you can look before moving on to the thermal part in your projects. Yeah, I hope this tutorial was helpful to you. Have a nice day.